Good morning, everybody. So last time we ventured into the fun of CMOS gates for logic. And we did static CMOS, sometimes called pull-up, pull-down networks, power ground networks, just a couple different names. People call them by. And it's overall, well, sometimes it can be complex. It's actually not too difficult to set them up. Essentially, we're um, designing a network. We've got our function that's coming out, and we have a pull up network and a pull down network. Pull down networks hooked to ground, pull up networks hooked to power, and then you've got your inputs coming in. That's doing the selection on them. And this is kind of, it's nice, it's not too difficult. Remember, the pull-up network and the pull-down network are, in essence, related to each other. Just like you could do this with Carnot maps, for instance, and the pull-up network is the one encirclements, the pull-down network is the zero encirclements. So you can get them by kind of flipping the network in some sense, right? Parallel things become serial, and serial things become parallel. So knowing one, you can figure the other one out pretty straightforward. Now, that's kind of nice. It fits a lot of our design techniques we think of. Anybody remember why it's static? Because it doesn't always stay the same. It's kind of a weird name, right? Because isn't it changing with the inputs? Static doesn't have to do with the fact that you can change it by different inputs. It means across all time. Once you set an input, it will stay at that value. There are other ones that can change and might only have a value that's good for a period of time. So when you change the input and there's a short period of time for it to update because there's some dynamics to switch to the new values. But once that switch is done, it stays static. If you leave it there for 5 minutes, it'll still be the same value. That is not going to be true for all types of logic we do. In some cases, there is a short period of time that the signal is valid for, and then it becomes invalid. And it turns out that those ones are faster. So, and you might be thinking, well, I like static. Static is good. I don't have to worry about timing and all kinds of other issues. And yes, so that's a nice feature. But the big disadvantage is it's slow. Now, the question is, why is it slow? Looking at this setup, can you figure out what's slow about this? So I do have inputs in two different spots, right? The pull-up network and the pull-down network. But what's slow about that? I mean, each one, they're parallel, aren't they? Is, but the problem is in that area. The question is, what is the problem? They are parallel. So in some sense, one hides the other to an extent. Now, this is a really important idea. How fast are these CMOS gates? So this is, there's something I'm hinting at. Are they both equally fast? No. Who's faster? The pull-up network or the pull-down network? How many people think the pull-down network is faster? I just heard that one. How many people think, okay, I got some votes. How many people think the pull-up network is faster? I know you're starting to think the important thing, right? What are they made of? And how fast do they operate? So, also in advance, the pull down network is fast, much. but it has nothing to do with the fact it's pulling down. What are these networks made of? One is P and one is N. It's PMOS, one's NMOS. Which one's PMOS? The pull up network. Therefore, leaving NMOS for the pull down network. Well, so we did talk about this one before when we first introduced this. What's the primary charge carrier for pull down? The electrons, right? And the primary carrier for the pull up, holes. Right, so remember, PMOS, which is power better, so it's just more efficient. But here's the thing, right? Think about speed for a second. Anybody remember well, actually, let's do it this way. Here's our P type as a symbol, and here is our N type, right? So this is PMOS, and this is NMOS. Anybody remember what this symbol in the middle is? Remember, this is actually the drawing kind of tells you how it's built in some sense. So what's that middle kind of gap area? It's a capacitor, right? Because we're trying to control by a field. Now, on each one of these, for the PMOS, the P versus N is telling you the channel you're building. So it's trying to tell you for the PMOS, I need to get a bunch of negatives up here and I'll get positives down here, which will create a P-type channel. And I've got P material on this and P material on that. If I put a P channel between them, it's all one thing. So now they're connected. Otherwise, I've got N material in between it, and I have that diode front to back, and I can't get any flow. And the same idea, that opposite happens here, right? I get a bunch of pluses up here, so I can make an N-type channel, right? All electrons down here because these two sides are N material. So I want a wire made, a channel made that does this. Now, think about how I get flow using electrons. Go way to day one, right? How do I get electron flow? I've got that whole lovely conduction band and valence band thing, Fermi energy somewhere in between, right? And what I want is something to get promoted up. And what we usually do when we're making our N types is we kind of added an extra little layer up here, which kind of raised the Fermi. But it was a small jump up, and then the electrons are free to move up the band. What happened when I was doing a P type material? Yeah, again, we've got this and we've got this, and we added, maybe I should do these in a different color, right? I added this one, I added the new band here and Fermi moved up. Right, this one, I'm adding a new hole, an empty spot, which is just above. Fermi moves down just in between the electrons, and an electron can go up to here and then move about and then fall into the next hole. And that makes it look like holes. So which one is doing more things at that? But hole, right? That P type, right? Because it's got to get promoted, move, and drop. That's how holes move. And you're not having just regular electron flow. It's really this whole series of little holes. So it's a lot more work. There's a lot more you need to be able to wait for something to pop up. It's just not as quick to move here. Um, this is part of it. Anybody else, when you're dealing with this on this capacitor area, I've got to kind of form this whole lovely thing up here. What's the equation for how a capacitor is governed? If I would say, what's the capacitor's equation? What is it? Yeah, that's easy. What's the speed?
area.
So that's building it, yeah, and that is correct. So we've got to be more specific. If I was asking like in basic physics, what governs the relation between your charge and your voltage and all that stuff? Q equals CV. I actually remember this one. So my physics teacher, when I first took this, and this was ages ago, he actually always wrote it this way because he claims when he was going through school that they drank the cheapest beer that was available to them. Big shocker. And he claimed at the time what they drank was a beer called Canadian Velvet, who supposedly their motto was Canadian Velvet is the queen of beers. Canadian C, Velvet B is equals Q, queen, right? So I don't know if it's true. I've actually subsequently took a look up and see if it is a Canadian Velvet, and I have not been able to confirm that such a beer exists. Despite this, I have not been able to forget that stupid slogan from an imaginary beer company since it was told to me 30, 40 years ago. So again, it's one of those stupidly memorable phrases that's actually quite helpful. Okay? So it's kind of a fun way to remember it as a mnemonic anyway. Let's take this basic equation and I want to take its time derivative. So I'm going to go this way now. What's the derivative of Q with respect to time?
Q is not based on R, so it's Q.
Well, it becomes Q dot, right? But Q, the charge can change over time, can't it?
Yes, but it's not.
And what do we call when charge over time is happening? Current. So I take the time derivative and Q becomes I. That's the current flowing into that capacitor, right? We're going to assume that our C is not changing. It's not always completely true. If it heats up or other stuff, it can change. But let's assume for the moment that we're dealing with a constant C. So then I just have dV dt. And I am breaking it up that way because I want to slightly rewrite this. And I'm going to split these. This is an old trick in integration land. I can split them and move them to opposite sides. So I'm going to take the dt over. I'm going to bring the I to this side. And I'm going to get dt is equal to C over I dV. All right? Now, this is my change in time. If you consider this C over I, this is kind of giving you an idea of what it takes to charge that capacitor, and this is telling you how long it takes. All right? So if I increase the capacitance of my system, what's going to happen to my charging time? It'll get bigger, right? Bigger capacitor, longer to charge. Makes complete sense. What happens if I increase the current flowing in? It'll decrease, right? It's on the bottom, that makes sense, a bigger ion. If you think about it, just use like a water analogy. The capacitor is how big the tank you've got. If I increase the flow into the tank, you're going to fill it faster. Okay, that kind of makes some sense. How about the dV? Now, it's kind of a weird one to you, right? If I increase the voltage, I'm going to actually increase the time it takes to charge this. You ever notice how most chips, as we're doing, keep dropping voltage? There's two reasons. One, if I drop the voltage, you drop the power. Right? So less power, less heat, all kinds of good stuff. But also, if I drop the voltage, I drop the time it's going to take to charge this.
But I always thought the cost was very similar to operating. And so we ask ourselves, well, if we add more voltage, it's more time to take the charge up because it's bigger.
Yeah,
Is what I always say.
sure. My basic point on just this is noticing a couple things. Number one, that voltage is related to your time. Okay? And that's a good analogy for thinking about things. Um, my point just being for Martha, number one, You can see another reason why I want lower voltage. It's going to take me less time to be able to achieve it, right? A little bit faster current does seem helpful, but gets into a little bit of challenge with the voltage too, since they are related to each other in some very direct ways. But obviously, I want a small capacitor. Now, here's the problem. My charge carriers are slower, right, when I'm dealing with holes. So if I want to make up for the fact that they're being slow, it means they're not carry things as quickly across the opposite side. So I need more, but to get more of them, you've got to make it bigger, right? Because I just have to add more of these into this. But if I make them bigger physically to have more of these carriers available to me, that means the capacitance goes. And this gets the original equation you were telling me about, which the capacitor has to do with its AFI. Okay? So in general, to keep them somewhat more reasonable, I have to make my capacitor larger for PMOS gates to get the same speed across them, so I have the same number of charge carriers because they have this longer route to become available. In general, it's about 1/3 the speed that they're traveling at, which means I need them to be about 3 times as big. That's a huge increase. So you think for similar sizes of these, my PMOS network is going to be 75%. That's huge, right? But here's the problem. As the capacitor gets bigger, what happens to how fast you can turn? Yeah, so it slows down. So I can speed up how fast I can carry across one state will, but it takes longer to get it to that full state because the other one was full in a period of time. Essentially, there's almost nothing you can do to make these fast. PMOS is just big. They are just not fast, right? They have their place. They're really good for transferring people, so I can't avoid it. But they're big and they're slow. Mhm. So if you could get rid of something, what would you to get rid of to make this faster smaller? I'd like to get rid of pull-up. But what's the problem with just coming across an app? How do you get over it? So what other ways can I get? Sounds like a weird question, but I mean, I want to get something. I don't want to use P1 transistors. Then I use okay. What's its disadvantage? Yeah, it doesn't transfer the power. So I'm going to get a huge drop on these. It's very inefficient. So I really don't like that. Right? So that means I'm generating more heat for no benefit. Because I'm going to get, somewhere probably a loss of a volt or so on this. It's just not my favorite, right? So can't really use that. Sounds like a nice plan, but unfortunately the inefficiency of power transfer is bad. What else can I do to supply power? What do we do with BJTs on the output? What is the first thing we do to supply power? So totem pole used transistors to speed them up. So that was a ultimate solution because with BJTs, since you can just slam current into those things, and you can make those stupid fast by nature. And with enough current flow, even though I lose some voltage, I don't really care because I got a lot of oomph. The disadvantage is I got a lot of oomph, right? It takes a lot of power, which means I generate a lot of heat. So, you know, This is almost a big totem pole, right? I have transistors on top and transistors on the bottom. I just don't like transistors on top. They're inefficient. So think before the totem pole. Remember how we had the open outs and we had some other alternatives? What did we do to supply power in those? We put in a pull-up resistor. Okay? So could I put a pull-up resistor? I could, right? Now, are pull-up resistors fast? No. Why are they fast? We resist the flow through. Plus, I've got resistors and capacitors. And the second you make a resistor capacitor system, you end up with a time constant. Now you've got this lovely little differential equation, and you get this time constant, which is related to RC. So I can, if I get a very small resistance, I can have the current growth, but the bigger the resistor to keep from getting too much current flowing, the slower the system is. Right? And you can directly calculate it because how's proportional to RC, right? 20, but in any, right? So we'll just take our RC as, okay, so R is bad for us. So that's another one down. Right? So I don't want to use the transistors, right? And I don't want to use resistors. I want to use BJTs, that's what we're trying to get over here, we get too much power. I'm going through almost everything. What else can supply power to me? A capacitor, very good, right? So I put in a capacitor that has a charge on it, right? And I could charge up the capacitor and it could supply me some power, right? Now, on that one, what's the disadvantage to a capacitor? If you do through charge time, what was your charge time? A discharge is not constant, is it? Right? So, uh, can I make it small? Yes. Yes. Therefore, can I make it fast, particularly if I don't put a lot of resistance on this, so I just slam charge onto it. Okay, so I can make this. How many alternatives do you have? You don't. So guess what we do? Right? So our goal is going to be to get rid of that. So we're going to get rid of this, right? I'm going to first do the bottom half because we're going to need something up here, and I'll explain why in a sec. We're going to keep our pull down network because we like our pull down network. It's fast. But, yeah, sorry, no puns. Kills me too. We're going to put a capacitor on that. The challenge is I have to charge that capacitor. But for a second, I do have a charged capacitor. Let's just see if this is going to work. If I have a charged capacitor and you put your inputs onto the pull down network, and there's a path that goes to ground, what happens to the capacitor? Just what happens to that whole thing? There's charge on top of the capacitor, at least initially. Right? I get a path here somewhere through this. I get some path that takes me to ground. What happens to that capacitor? So it discharge the capacitor. Yeah. Right? So what do you see on the output app? The table, what I put up here, I've got to copy that. What do I see on that? Should be zero. And if there's a path to ground through the pull down network, what do you want to see? Zero. Zero. Oh, that's good. Well, what happens if there's no path to ground? Then in goes up and hits the there is. If there's no path, this is gone. So what does that output see?
It should
It sees charge, so it sees a 1. What do you want to see if there's no 0? A 1. So if I can get a charged capacitor there, it works. Does that make sense? How long does it work? The charge lasts, right? Now I'm only small, so how long is it going to last? Which is good. It's actually true, it is good. Why is it good? What do I want? I want a very fast system. What does this system work? What does it require? You gotta be very fast. Right? This system only works if it's fast. Okay? And it's not gonna last, so it's not anything it's dynamic. So this is going to be a dynamic network. So, and it will only work if it's fast. Now, think about is that a question for me?
I'm saying, more like how it is. So should the charge down to be small so it's fast. But how does the capacitor powering down give us an advantage in this?
Because it forces you to be fast. And we want its best operation, right, happens when this is very, very quick. And I can speed this whole thing up by making it smaller. If you need a little more time, make the capacitor a little bigger and it slows down. But as long as ideally this operation, I make that capacitor really small, which is easy to build as a structure. And it essentially gives me a fast system. Because it will only work if you are fast. Because if you are slow, it's not going to catch it. Now the disadvantage is you got to go fast. But that's what you wanted to do anyway. So far so good. Yeah.
So
So F is on as long as there's nothing discharging that capacitor, right? Because that PDN is going to discharge really quickly. We're making a very big path to ground. So that's going to be your easiest discharge path. And we'll go out into a next network. So it's going to go into a gate, which is basically the other side of the capacitor. Right? So you're just sloshing the charge to another gate. Right? So it'll hold there. Right? There's no real easy drain. You will get some drain, but if you have a path to ground, it'll discharge that tiny, tiny capacitor really quickly, and it won't be able to open the next gate. Does that make sense?
So the advantage that you can power and can discharge the capacitor to make it where it wants to
And it forces us in this sense that it forces us to act quickly in all of our designs, right? Which could be you could think of it as an advantage or a disadvantage, but it is what we want, right? It's challenging to be able to react quickly to it. But that's what we want. We want to react quickly. So the operation of this system requires fast action on our part. And we want to do fast action. So that's why I'm saying it's an advantage, right? It's also a challenge, but I encourage you, think of every challenge that at least works in the way you want as a gift. When I finished up my PhD and I started my first research professorship position, and I was working on this, I got I've been working on some connections with medical hospital nearby. Near Christmas time, one of the doctors calls up and he's like, I got a real big problem. We can't get this thing to work. And my reaction was, that is the best Christmas present I'm getting this year, right? Because the second an expert in the field says, I can't get it to work, that means that's job security, right? It's a problem. I can solve that. right? And essentially, I solved the problem for that doctor, and I've been working with him for 20 some odd years now. And because I could solve the problem. Problems are a gift to us, right? Other people look at problems and they're unhappy, but your job exists because other people can't figure out how to solve this and we need to, right? So in this particular case, the problem is leaning to the side we want. In order to make it work, you gotta go fast, and what you want is to go fast, right? If the system only worked if it went slowly, right? Then that would be like a problem that doesn't have an advantage. I could get the solution to it, but I could never make it quick. But I wanted something quick, and this is the only technology that works well if it's fast. So that's why I say it's a gift to us. Because it does what we, yeah, you gotta figure it out. But who cares? Right? That's good stuff. Does that make sense? Now the challenges, right? So obviously if I have a charge capacitor, it works. Now we got to ask the question, how the heck do I get a charged capacitor? Yeah. Magic. I solicit Tinkerbell and she comes in. Yeah, it's sorry, my bad sense of humor. What does it take to charge a capacitor?
It takes voltage.
Yeah, and some time. So I have to have a charge period and a discharge period. Does that make sense? Okay, so since I now have two periods, do we have any type of a timing thing that has two values? Regular intervals. A clock. It's got a high value, low value, and it alternates, and we can make it as fast as we stupid want. So we're going to take our clock, and we're going to make basically a evaluated, don't evaluate it period. Right? So we're going to have basically two cycles, a charging cycle and an evaluation cycle. And you have to do this across a clock period anyway, so this is no problem, right? We have to have, since we're going to go through the computer, we're going to be evaluating a function, but then we have to put it in register to hold it. And it will then come from the register and go through the logic again with some stuff. So I'm going to take the period when I'm storing this and memory is doing its thing. And while memory is doing its thing, I can be charging that capacitor. You use your clock cycle anyway, just to pull it into storage, to hold it, to get it to the output and ready to go for the next cycle. And you, does that make sense? So it looks like I'm doing something I hate, but I really don't have a choice. I have to supply power, so what's the only thing that works well to supply power? Yeah, PMOS is the only thing I can do here. But instead of a whole network of these, I'm only going to have, and I can completely hide its slowness. I'm going to hide its slowness because I'm going to hook this to my clock. Right? Now I could hook it to clock or clock bar depending on how you want to time your memory. I'm just going to say clock here because it's less work. Right? But if I put clock on here, when clock is high, what happens to this gate? It is, right? Yeah, remember PMOS, I want a negative. So if clock is 1, I'm going to prove on that, which means unfortunate a negative on the other side, which means an N channel. I want an N channel. It's off.
Okay, so, yeah.
So that circle tells you it wants it low to be on. So when clock is high, that gate is off, which means we just have our evaluate cycle. Right? So under this setup, right, clock, has two choices, 0 or 1, and we said if it's 1, we're really doing our evaluate. What happens if clock is a 0? Exactly, right? This connects, and now I got power flowing in. So this is my charge. Okay? Now this fits all within one cycle. That's exactly what you need for a computer. This is sometimes called pre-charge evaluate because I pre-charge it before I evaluate it as a charge and a discharge. It's also called dynamic logic. Since I only have one PMOS in this whole thing, and it fits exactly in, this is stupid. That's awesome, right? We have the really fast pull down network. They only have one slow tape, but I've hidden it completely by my clocking. So the time when it's on, which is the slower thing, is 30 times you're doing is trickling charge into that capacitor. So what do I get? The whole time is just charged. That is easily going to be handleable. So I don't have to make a ridiculously big one and then falling fast. Right? And the second we go to the actual calculation, which is the thing I care about for me, it's not involved. So no worries on it. So this is crazy faster. Almost 3 times faster than the previous one. That's a really big advantage in computers. That makes sense how it works? So this is step one. This is called footless. Not to be confused with some dance movie from the 80s, Footloose. This is footless because it doesn't have a foot. Okay, so now the question is, what has a foot, right? Besides the great phrase from Sherlock Holmes, something is a foot, okay? Yes, I'm trying to put in stupid puns because it actually shows you have better recollection if there's some dumb joke that associates it in your memory. So there is a madness to my method. All right, the foot. Where is the foot on you? The very bottom. So it's talking about the very bottom. Here's where the challenge is. Right now I've got this turning on here. So technically speaking, as I am trying, as this one is on and I'm trying to charge this, is it possible that these inputs could have a pathway to?
Yes.
So is that a good situation? Now I can make this one so it charges faster than what drains, right? Well, that slows the network down and other associated stuff. So I could definitely do this if I want to make it easier, design it a little bit smaller. But ideally, I'd like to turn off the pull down network. Make sense? So this is where I want to add a foot. Let's see. This hopefully will show up nicely. So we remove that, and now I'm going to add a foot. Now, what I want, this is again an N type. N types are small and fast and no problem.
This needs to be attached to clock.
Yes, it does have to be attached to clock. Should it be clock or clock bar? So now we want to think on this one, right? For this one down here, right? When do I want this one off? When we're charging, which is clock is equal to 0. And if I hooked clock here and it's 0, what's going to happen to this thing? Right? This is an N. So if I put a bunch of minuses on here, hooking it to 0, I get a bunch of P's. So I get a P channel, not an N channel, so this is off. So if clock is 0, this is off. If this is off, it's disconnected from ground and this whole network disappears. Does that do what I want? It does exactly what I would like, right? So clock is the right thing, right? It's really easy, if you notice, no matter how smart you are, it is really easy to get things backwards. Which is why I suggest you just do the simple one. If you're doing this all the time, then just getting ingrained in you. But if you haven't done it in a little while, just walk through the flipping logic. It takes you an extra 5 seconds, and you're guaranteed to get it right instead of a knee-jerk error. And then if this ever becomes one during the evaluate stage, this opens up. So when I pull down network is fine. It does that very fast. Who cares? Creates no. So this is a footed system. Right? It's got the foot on it. That extra clock that connects, disconnect, makes that capacitor a little more efficient. Does this make sense? Okay. So far, so good. Now we've got our next situation that's coming in, right? We've now got a good system. This is a fully workable system. So the only question left is, what's going to happen when this whole thing is imagine, can I, for instance, cascade this? This is one level of, can we do two levels or into many? Right? Now, what if you want to go to multiple stages? Right? It will latency, it adds something else that's the more places it has to go, right? This is what's called fan out. So it has to go to multiple locations. What does that do? How much oomph do I have behind it? Hey, I've got a composer, so that's going to get split. So if I have to go to a bunch of places, what's going to happen? Add right? It's going to spread out. And if you spread out the finite amount that we have, then you're not going to create any good. Right? It is also possible with that kind of too much stuff out there, right? Whole digital. When you're charging it, I'm also spreading stuff to those. Right? We also run into this situation when the next stage is called the same clock IMAP. It's going to open up. And if it's not hard pushed here on the output, it will, across that resistor capacitor network, it'll take a little while for it to charge up. It might be too slow to reach the next stage. So the problem is most of these dynamic ones, you can only do one level. Now, I could design a network that implements a full function if I really wanted to, so I could do it in one moment. But it would be nice to be able to do two levels of logic or several levels of logic because a lot of times designs are much cleaner if they're multi-level, as opposed to trying to figure out one bit out of the X. That makes sense? So I need one that I can cascade. This does not do a great job of cascading. So far, so good on it. So what would be a way? My big problem is, if it's fan out, I don't have a strong enough push. Right? If I were to give it a little bit extra push, it would also go faster than the next one, which would speed up the next state. And I could actually use some type of a buffering device to be able to prevent an early discharge or other types of problems, right? My charging would be buffered by that, so it would only go to this location instead of spreading out. Lots of good things. Does that make sense? So what can I use as a buffer here? Because my problem is this output area, right? I mean, whether it's fan out or, speed or early discharge, all kinds of other stuff. I need something to block this from just going out and when it needs to give it a push. Okay? So what could buffer? Yeah, and in particular, what if we put a buffer emitter, which is just a transistors hooked in a quick discharge power situation, so that I'm pushing it a little. on here. And the fastest, easiest one to build, as we have seen so far, is an inverting buffer. That's very simple to build. Now, this, I have with an inverting buffer, it's a very small thing to add on. It takes a couple transistors to build, so plenty fine. I don't have any problem with fan out. I don't have any problems with early discharge. Got all the power and warmth on this. That little tiny push from the capacitor is enough to open that up. Right, and it's right next to me, and it's good flow and a push, which means I have no cascading. And one will fall, and it'll be enough with that extra little push to make the next one, so I can cascade. So that idea of one thing falling and tipping the next one fall, and you can cascade them, what does that? Dominoes. So this is called, when you add that buffer in, it's called domino logic. Yay! There you go. This is really what you do. And the idea is you can cascade them. And a little bit of that extra buffer created. Still plenty stupid fast. You don't have to worry about any of these other problems in here. Takes care of the timing issues and everything else. And that's what buffers were built for. Right? And they're small and they're fast and all kinds of great stuff. So yay. Most computers are built off some variant of domino logic. And there's a lot of variants. Some people move the capacitors into the pull-down network, so there's all kinds of crazy stuff you can do with these ones. There's shared charge networks. There's all variants off this. What I wanted you to do is, if you understand how to do the original static CMOS, it's not a big jump to go to dynamic logic. In dynamic logic, you just recognize, oh, it got this kind of problem, right? And therefore, I just add the buffer and you get basic domino logic. And then everything after that is just efficiency tweaks. But you've basically got stupidly fast logic at this point. That can be cascaded plenty fine within a clock situation. So you can do whatever you need. Feel good on it? Okay, so this is dynamic logic. We have a little bit more time, and I want to show you one last important idea, which is not a dynamic setup. It's actually a really elegant CMOS technique that's independent. So if we feel good with this part, I'm going to move back to a static logic. Good? Okay. So now we want to move to another type of static logic. And we're going to take advantage of some properties here. So if, and we've kind of talked about this a little bit, if I had a PMOS gate like this, I just wanted to consider this, and I said, hey, look, what if I considered the behavior of this, and let me call this some little S here, and here's A, and here's B. Now, I'm going to consider A my input and B my output. So just twist the gates so that's kind of the natural direction of it. So S and A I can think of as inputs, and B I can think of as an output. If S is a 0, what happens to this gate? It's open because a 0 puts negatives here, it creates the P's, that's my P channel, right? That's what a PMOS wants, a P channel. So this is active. So then what's the relation between A and B? Yeah, whatever A is, B is. We agree? Okay. What happens if S is a 1? Right? Yeah, the gate is off, right? Because now it's power, so it puts a bunch of charges here, so it puts a bunch of minuses. That's pushing an N channel, right? I don't want an N channel, right? That makes it actually worse for me. So what's the relation between A and B? B is, yeah, high impedance connection, right? So we put a Z here, meaning from what you've shown me, right, it's floating. If you attach something else onto it, it'll overreach because I'm not pushing anything like this. Make sense? Okay. So this is kind of a nifty situation here. What if I consider similar setup, A, B, with an S on here, right? NMOS now.
A is B. A is B. So
Okay, so if S is a 0, right, what's on the top?
if X is 0, then
It's, it's minus, right? Because if it's 0, remember, from ground, that's electrons are flowing up, or positives are going down, whichever way you want to think of it. Right? So I'm ending up, I've hooked it to the minus source if it's zeros. So it's all minuses here, which means it's all pluses here. What type of gate is that? It's an NMOS. NMOS wants an N channel, but I just made a P channel. So it's off. Yeah, so this is going to be Z's. All right? And what's going to happen if S gets a 1? It'll be on, right, for the exact opposite reason. I get pluses here, I get minuses, yay, I got my N channel, now they're connected. So A is able to go to B, right? So 0, 1. Okay? And I look at this, I go, you know, this one over here, right? Let's just add a little modifier, right? A is equal to B, but remember, this one is strong, this is good. But this one, I'm just going to put a little asterisk by it. It's weak. It doesn't really do a great zeal test because P-type doesn't really carry it great. All right? Now, how about on this one? I mean, does an N-type carry a good 0? Yeah, strong, right? How about it's 1? Yeah, not so much. It's kind of weak, right? So this one does a good 0, and that one needs a good 0, and this one does a good 1, and this one needs a good 1. Right? So, but they're kind of in the opposite stage. So what if I made this S bar? Right? So now I would have, if I'm looking at this and I'm dealing with S bar on here, well then, right, let me just put S so I can compare them. Right? If S is a 0, S bar is a 1, so I get my 0, 1 star here. And if S is a 1, S bar will be a 0, right? That's, yeah, right? So, you know, S bar is a 0, so that's off, and therefore I get my Z's. Now they look compatible. So what if I were to connect these?
if we connect those,
Well, look at their tables. Do they look compatible? Yeah.
but we get strong 0, strong 1.
I get strong 0, strong 1, exactly. Okay. So, and I've got it turned off when I want it off. So we'll often draw this. There's a couple ways you could do it, but we usually draw one, and here's your other, and here's my A, B, and here is, I can do S, S bar, or whatever makes you happy for it, right? But it kind of looks like this, right? Like a nice little square symbol. Oops, I just overshot. I just think of it, two lines, boom. Right? You can kind of see this, right? Square with the lines. I did such a horrible job drawing that. Um, that's what we call a transmission gate. Now, there are a couple ways. This is one way. We tend to draw it this way in logic. Um, it also has what we call the bow tie form, which it kind of looks like those, it can flow nicely double. We put the 0 on whichever side. It could be top or bottom, telling you where the 0 here is. Right? And the idea is that it's just letting things, it flows better than just a regular gate does, but has similar behavior. You'll also see some of them I designed so that it literally will flow either direction equally well. I make them truly symmetric, so it doesn't matter which way it's going. You'll often draw those as what we call a double bow tie. Um, So I'm specifically, if I'm drawing this, I'm trying to emphasize the fact it'll flow either direction equally well. I'm just mentioning these because you'll see them. I am only going to use this one because that's really common in logic. I mentioned the other ones because you'll see those other symbols. It's the same stupid thing, just depending on whether you're giving a really strong double connection. I've seen some people do this one and mean the double connection. Right? What you're really saying is transmission gate. Really good connection, both power and ground, evenly flows. If you have this, you're really emphasizing it doesn't matter which direction it flows. It's pretty symmetric, left to right and right to left. Okay, so far so good? Okay, so now we've got kind of our symbols and our things. The question is, what can I do with this weird thing? All right? So, now, I could come in here and specifically hook this up to be able to have them, the inverse be automatically applied, because that's ideally what our situation. You could technically hook different things to each side, but that's kind of not as pretty. But this is only 2 transistors. If I add the inverter to flip between them, then I'm still only dealing with 4. This is a very small gate structure, right? But this is also nicely controlled as, anybody tell me what's going on with this? This is a gate. You might have seen in digital logic, hopefully. This is called a tri-state gate, right? So a tri-state gate could be built as one of these or the other, or as a transmission gate. Right? There are 2 forms to tri-state gates. Right? And really it's just a control which is either operates off of positive or negative. And if the control is satisfied, so if it's a 0, it's open. If it's a 1 on this one, it's closed. That's essentially what we just did here. And the third state is Z. I just make or break the wire, connect or don't connect the wire. Right? Similar here, except you're just saying high is open. So it's really just which way you hook a transmission gate. This is really important because it's used for a number of different things, one of which is buses, which we've already talked about. This is a great way. With one simple little gate, I can give you the control signal is, are you allowed to talk? So think about when you typically have a network or a bus situation, there's usually some controller to the bus that's saying who's allowed to talk at the moment so you don't get crosstalk on your network and shorts and all kinds of other problems. Right? So one way you could do it is the bus controller could send a signal saying your turn to talk. They give you a token, they give you a high line, whatever, which tells you your turn. They can send your address and you can decode that. Right? Lots of these options. If I hook that signal to one of these tri-state gates, I then connect my output signals to the bus. And if I'm not getting that signal, I'm disconnected from the bus. So in one gate structure, I've got a very nice way to connect to the bus, don't connect to the bus. That can be easily handled by a controller to identify when you're allowed to speak, and then I cannot mishandle this. It's an easy way to build that protocol. So, very nice way to handle buses. You'll see this a lot when you're interfacing computers. We do this type of thing. There's a second type of device, though, that this is used for. Anybody remember what the other device is besides a bus? It's like a bus maker in a single device, but it has other uses. In essence, it's something that could allow several things to come in, but only one of them to get talked to. It switches between them. MUX. So a MUX, a multiplexer, essentially is built using these type of transmission gates. So imagine I'm going to take the most elegant little small MUX, which is just a 2-input MUX, 0 or 1. It's got an output and it's got a controller. Let's think about how we can build this. So I want, when it's a 0, I want this one to connect. How would I do that with a transmission gate? When it gets a 0-1 control, I want the transmission gate to open. So here's my transmission gate, right? Remember, S, and if S is a 0, I'm going to oversimplify my table. If S is a 0, I get an A. If S is a 1, I get a Z. Just kind of condensing the table down to make it prettier. And we know it's a strong on both 0 and 1 because we hooked those two together. Right? So I want to let this one through when it's a 0. What do I have to hook up to the two sides here? Yeah, so if I hook, I hook S here, what do I hook here? S bar. Right? And then this one is kind of my 0 input line. That make sense? All right. I also need a 1 input line. I'm also going to use a tri-state gate or a transmission gate or however you want to think about it. All right. Now what do I have to hook to this so that a 1 opens it? I want the exact opposite. All right. Now notice kind of nicely these two are the same thing. So I can kind of hook them together. All right. And just hook that to S bar. Which, if we want to think about it, I can just draw my inverter this way, which means S going into the inverter. Fair? And this now gives me my MUX. And I just hook these two together, and there's my output. Because they must be all at the same time. So these transmission gates let me build a multiplexer really easily. So far, so good? So can I do anything with this logic device? The multiplexers give you a nice way of doing logic design. What does it do? So remember the basic design, right? Everybody remembers Carmel maps, right? Which we've kind of talked about. Is that the only logic design in town? Now, what else do I have? There's a lot of design techniques, right? So you actually get 4 logic designs out of Carnot maps. Step to the side here. So this is my remember back section, right? So K maps let me do kind of I could encircle ones. What happens when I encircle the ones and locate something? I ended up getting a nice canonical form. Remember what that one's called? Sum of products. That was a nice, easy way because I could use NAND gates and build it. That was the encirclement by trick. Any other questions with Carnot? What if I encircled zeros? What did I get? Product of sums. And that was NOR gates. And notice this is independent of whatever you build. Okay? We could build these with CMOS, you could build them with BJTs, we got options. I could use these to actually even design my pull-up, pull-down network or my Domino logic setup or whatever I feel like. And then I would probably start with static and then I could easily morph it into dynamic or dominant. Okay, these work nicely. Anything else I could do with these? So 2 other tricks, which is all based off one idea. What if I went into my Carnot map and I flipped it? I made every one a 0, right? Then I could still do both of these now, right? On that negated form, right? So I'm just going to kind of combine these and say, what if I flipped, right, my ones and my zeros, right? And then I could still do each of these, but this is kind of a negation. Now I can fix that once I can now do my encircle ones and circle zeros just like I did before, except they're now flipped. What I would get is the negative of my function. I could just run that into a right? So I could also flip these and I would get, the ones were actually originally zeros. So if I flipped them, right, the zeros turned into, I'll put the zeros, right, in parentheses, just remind us that's where they came from. And if I encircled ones, I was doing the zeros. I'll still get a sum of products type expression, but it's on the negation of it. So we call it negated sum of products. So I could encircle, in essence, what were the zeros, but now they look like ones. I'll get the negation of the function, and I just run it into a not gate. Now you might say, why the heck would I want to do that? That's a long extra one. Yes, but it allows me on zeros to get a sum of product looking expression, which means to build the zeros, and sometimes the zeros are simpler. But if everything else in my logic is using NAND gates, I want to insert a bunch of NOR gates. I'd rather build it all with one technology, so I can just flip it. Right? The zeros become ones, I build it with NAND gates, and I just add one extra NOR at the end. And now I took care of the whole thing. So I could handle the zeros in essence using some of products. Because sometimes there's like only a few zeros, and so encircling them's really easy. And to get the ones, it would be some crazy collection of them with 20 encirclements or something stupid on a big design. Right? So sometimes we just want to avoid that, but we still want to stick with encircling ones. So we flip them. So I could get the negated sum of products, which allows the ones to go by NANDs with a NOT gate at the end, right, to flip it back. And the same thing, the ones, if everything else was a bunch of NORs, they're now zeros. which means I get a negated product of sums, which means I can stick with NOR gates and a NOT to undo my flipping. So you technically get 4 techniques that you can do, depending on what you want to encircle and what that gate you want to use. All right. So this was one option. All right. The next one that's often introduced is related to what we're doing here. All right. So we could do, usually it's like an encoder logic or a multiplexer logic. Anybody remember multiplexer design technique? This is one I always emphasize. I don't know if you didn't have me, you may have seen this. But if you didn't see this, you're going to hate your own teacher for not showing you this. This is like one of the most beautiful, easy techniques in the universe. This makes Carnot maps look like a gigantic pain in the tuchus, because they are, right? But they're still beautiful. So let me just talk about Mach's technique for here for a second. And I'm guessing people don't know Mach's technique. So let me show you a simple way. We'll do just a simple 2x2. Let me say I have A, B, and C as my output. 0, 0, 0, 1, 1, 0, 1, 1. I'll let you pick. Sequence of zeros and ones for C. 1, 0, 0, 1. Is that good? Okay. All right. Now, you might try to recognize this or other stuff, but let's do what Mach's technique is going to do. First off, it's going to split off the least significant bit. And it's going to use anything other than the least significant bit is going to be its address. All right? So this A is an address. It's either a 0 or a 1. So on my mux, the control line is A. A can be a 0 or a 1. That's my 2 options. If A is a 0, now my output needs to be C. That's what we're trying to design for. If A is a 0, I'm coming through this line. So we look at this, it's a 1, 0. How does that relate to B, the only thing I haven't used so far? It's not B. Boom. Take a look when A is a 1. I'm here. Yeah, C is B. Boom. You're done. You have now implemented that function. We just did a complete design of whatever you picked, and it took me like 10 seconds. See what I'm saying? Mux design just kicks rear. And remember how easy I can build this Mux? So transmission gates make very nice, easy logic. What if it's a bigger function? Well, can I build a larger Mux and smaller? Yeah, all I have to do, just as a side note, I can cascade them. I got a smaller 0, 1 here, right? With, I'm going to put L. I get 2 of them. Both hooked to L, right? And I just cascade them in. 0, 1, I'm going to put M. I'll explain it in a sec, right? So if M is a 0, I'm reading from this. So if M is a 0, L is either a 0 or a 1. And then F, right, my output, if it's both zeros, it'll be, I haven't used any of these letters, so I'll call it A, B, C, D. F gets A. Right? If M is a 0, I'm reading from this, and L is a 1, B goes all the way through. Right? If M is a 1, I'm reading from the bottom gate. Okay? So if M is a 1 and L is a 0, then this line gets through, so C goes out. And if M is a 1 and L is a 1, D goes out. So notice M is the most significant bit, L is the least significant bit. It's the easy way to kind of remember that when you're building them. And this is 0, 1, 2, 3. That is your larger mux gate. You just kind of. So I can build as big as you want doing these binary trees. Now I got like 30 seconds, so let's do a real quick larger one. We did one of these, let's do A, B, C, and now I want an output F. I'm going to number this a little bit weird because I'm going to anticipate that I'm going to do my design using Mux style. Anybody want to give me an F? Okay, you like it? Awesome. So again, this is going to be the one I'm going to hook to the inputs. This is my control AB, giving me my most least significant bit. And then all I do is hook to the input. When the input is on 0, I hook, well, F is the opposite of C, so I'm going to hook C bar to it. So on my mux, and I've got A, B together as my 2-wire controller. 0, 1, 2, 3. On 0, I hook C bar. All right. When AB is 0, 1, that's input 1. It's 2 zeros, so that's a 0. Just always hook it to ground. When AB is 1, 0, this is the same as C. So 1, 0 is 2. So I hook C to it. And when I've got 1, 1, this is just always powered. So I hook it to power. Function design. You could not do it that quick any other method. I submit to you much design. It's one of the coolest design techniques that's out there.
And to saying AB is a
It's an address line because it's a 2-bit. To control 4 inputs to a mux, you need 2 wires. Fine. So I'm just specifying the order I put them in. I put them in curly braces, which is the sequencing command inside of Verilog. Fine. So I'm just saying, treat this. This is my 2-bit wires control wires coming in. So I needed most and the least significant bit. Most significant, least significant. Whatever is after the first one, that's your address commits. And you can see exactly how much you need. You just group them in pairs and compare them to C. With the letters sticking the outputs in order. You're done. That is pretty nice. So, quick question, why don't I only do this? This does not protect against any glitches. K-maps protect against glitches, this doesn't. But what protects me against glitches in this situation? Memory, I synchronize it. This is actually how FPGA works. This is your cables you're copying down. It just gets the function and copies the cables down. It's got glitches all over the dumb spot. If you time it, glitches only happen at certain points, so you just don't read it when it can glitch. Well, all glitches gone. That is the basis of FPGAs. It is much easier. Transmission gates make it very nice and easy to build these things. No special logic. It's kind of cool, right? I guess that's why I'm doing this. So, if you have questions, as always, you're welcome to ask me. Have a lovely day. We have gone through our basic how we build things out of different type of object. Hopefully we all feel warm and fuzzy about this now. Yeah. Um, so, for example, I thought there was one that used transmission gates on it, and I thought there was one that used the pull up, pull down handlebars. So you can check them, but I believe the stuff we've done both between the two do this. You should see I'm pretty sure the transmission gates. But if there's something else, you are welcome to talk about this. Let me just stop the video. And then, I don't think you want to get recorded.